So, lecture we are going to discuss the orthogonal properties of the Bessel's function, which is of the form Jp lambda and x, or let lambda n be a positive zeros of some fixed Jp of x, where p is greater than or equal to 0, then prove that integration from 0 to 1 x Jp lambda mx Jp lambda nx dx is equal to 0 if n is not equal to n, 1 by 2 Jp plus 1 lambda n square if n is equal to n. Or that is another ways to represent the same statement. It says that prove that the function Bessel's function j n j lambda n x are orthogonal on in between the closed interval 0 1 with respect to the weight function x. So this is the weight function x, where lambda r are positive zeros of some fixed Jp, or that is the Bessel's function for p greater than or equal to 0. So this is known as the orthogonal property of Bessel's function, that is j p lambda n x. Let us try to discuss the proof of this statement. So let us note that this Jp, that is the Bessel's function, is the solution of the Bessel's equation taking the time. Yes, so proof. Note that this Bessel's function is the solution of Bessel's equation of order p, that is x square plus y double dash, that means x square plus y double dash plus x y dash plus x square minus p square y equal to 0. If I call this as equation 1, then it must satisfy this jp of x, that is a Bessel's function must satisfy this equation. So we'll have x square jp x double derivative of the Bessel's function x into jp of x plus x square minus p square jp of x is equal to 0 for every x belongs to r minus 0. This is true. I may call this as equation number 2.
Sir, sir, derivative is over j or p of over j or p?
X is with respect to x. The differentiation y double s. This is jp of x. That is a Bessel's function.
Okay, sir.
Y double s, which is a differentiation with respect to x. Double derivative. So this is also differentiation with respect to x. Let a and b be any fixed constants. I consider a and b are the fixed constant, and consider u of x will be jp of ax and v of x will be jp bx. I'm considering these two functions as ux and vx. Then this u and v also satisfies the equation r because it is of the same form. Instead of x, we have ax. So then what we can have u double dash plus, I can say x square u double dash, or I can just write down that instead of x we have ax here. So that's why I can write down from equation 1 we have a square x square. So instead of y double dash, I may write down u double dash of x plus ax u dash of x plus a square minus p square u of x equal to 0. Now if I divide both sides by a square and x square, I divide by x square both sides. Therefore, this will be a square u double dash ux of x plus a by x u dash of x plus a square. This is a square x square is there. I forgot x square to write because it is x square minus p square. So it is a square minus p square by x square ux equal to 0 we have. So this is the things we got as 0. So now I may start with this side, that is y u double dash plus 1 by x u dash plus, I will start with now u double dash plus 1 by x u dash of x plus a square minus p square by x square u equal to, we may write this is by putting the value of this u double dash. What is u is jp of ax. So if I differentiate this two times, the first time we will have u dash will be jp dash of ax into a, because the derivative of ax will gives you a. When you differentiate second times, it will gives you u double dash will be a square into jp double dash of a. So if I use that one, this quantity will become jp double dash ax into a square plus 1 by x jp dash ax into a plus a square minus p square by x square jp ax is there. So if I multiply and divide by x square here into this term, that is 1 upon x square. If your x is non-zero, then this is x square a square jp double dash of ax plus 1 by x. If I can say it is, instead of 1 by x, we have now x into a jp dash of ax plus a square x square minus p square jp of ax, and this is x square into 0 due to this one, because we have this first equation, or I can say from this one, that quantity will become 0, so therefore this is 0. So hence we have u double dash plus 1 by x u dash plus a square minus p square by x square u equal to 0. Similarly, one can also show that v double dash plus 1 by x v dash plus b square minus p square by x square v equal to 0, due to that we have assumed that v equal to this jp of bx. So instead of a, we have now b here. So we'll have this two. I will call this as equation number, which number it is there, 3 and 4. Now I multiply the equation 3 by v and equation 4 by u, and then subtract from each other. So multiply equation 2 by v and equation 3 by u, then we subtract both of them. So if you do that, then you will have u double dash v minus u v double dash, because that is the things we got. You multiply this equation 3 by v and this is by u, so that is u double dash v minus u v double dash. We'll have this plus 1 by x, then you will multiply this is by v, that is u dash v minus v u dash plus this is uv. You will have, when you multiply this is by u, this is uv and this is also uv. So this two property or these two terms will be subtracted from each other, and this is p square minus x square is the same term is there with the same sign. So if you subtract, then it will cancel out. So the left quantity is a square minus b square into uv equal to 0. Now if you can rewrite this one, this I can rewrite as d by dx of u dash v minus u v dash plus 1 by x u dash v minus u v dash plus a square minus b square uv equal to 0. If you multiply this equation by x, not now, multiply by x. If you multiply this equation is by x, what we can have is x into d by dx u dash v minus u v dash plus you multiply this is by x, so this is u dash v minus u v dash plus a square minus b square x into, this has to be multiplied by x into uv equal to 0. Now you just observe what is this quantity, this 2. That is x as it is, the derivative of this, and then derivative of x which is 1, and this term is as it is. So this is actually d by dx of x into u dash v minus u v dash equal to, if I take this quantity on the other side, then it will be b square minus a square x into uv. Now integrating both sides with respect to x in the interval minus 1 to 1. So integrating on minus 1 to 1 both sides, we get b square minus a square integration from 0 to 1 x uv dx. That is, I have written this side quantity first and then this. So integration of this derivative will gives you this term, but the limit is from 0 to 1. So that's why this will gives you x into u dash v minus u v dash. A limit is from 0 to 1. So when you substitute 1 and when you substitute 0, all the things is 0 because 0 into anything is there. And when you substitute 1, this will be u dash 1 v1 minus u1 v dash 1. So hence, what is this u and v? Let us substitute this value of u and v. So therefore, b square minus a square integration from 0 to 1 x into jp of ax jp of bx dx is there. And this will be a u dash, that is at 1. U is, we know that is jp of ax, where x is 1, so it is jp of a, z dash p of a, then j dash, sorry, jp of b, because your v is jp of bx minus u, that is u, that is j p at a, and v dash, that is a derivative of this, and then substituting. So the derivative is b into jp dash of bx. So that's why it is b jp of jp dash of a. Now there will be two possibilities are there. If this m, and I'm taking this a as, what is the, let us see what is the we need to prove. According to we can work out. So I need to have, this is jm and jn. So that I'm substituting the value of a and b here. So now let us take a is equal to lambda m and b is lambda n. Be a positive zeros of Bessel's function. Why we are taking it as a positive zeros? Because at that point this quantity will be 0. That is jpm. So whenever this 0 is there, this function is 0, this is also 0. So we'll have 0 in that case here. So that is the Bessel's function jpm. Then if it is 0, will gives you jp at a, that means jp at lambda m is 0, and jp at b, which is jp at lambda n, will be 0. I will call this as equation number, I think so it is 5 and 6. This is 5 and this both equation as a 6. Now there will be two cases. Case number 1 where m is not equal to n. Another case is m equal to n. So now case number 1. That is, if m is not equal to n, lambda m is not equal to lambda n. That means these two things are not same, or I can say a is not equal to b, whatever you want. Then from equation number 5, that is this equation. What we can get from that equation? That means this side we will have b square minus a square integration from 0 to 1 x into jp lambda m x jp lambda n x dx equal to 0 because of equation 6. Because this quantity is 0 and this quantity is 0. So you may write as a reason if you want, because of 6. So finally what we got, this a square and a and b is not same. So that means this quantity will, so I can divide both sides by a square minus b square. So therefore we can say that this is integration from 0 to 1 x jp lambda m x jp lambda nx dx is equal to 0 because a square is not equal to b square, because a is not equal to b. So I can divide both sides by that. So that is the first quantity that I need to prove here. That is, if m is not equal to m, the answer is 0. If m equal to m, I want to prove that this is this. So for that, let us take the case number 2. So case 2. If m is equal to n, That means lambda m is equal to lambda n. That means A is equal to B. Then equation 5, that is a square minus b square integration from 0 to 1 x lambda p ax lambda p dx will be a jp dash of a jp b minus b jp a jp dash of b will have. Now we will divide this a square minus b square. But now what is the situation here? Is this a square minus b square is 0. Okay, so it is the indeterminate form which we have. If I write this is in this form, if I write down this is into this form, oh sorry, it is b square minus a square, not a square minus b square. It has to be b square minus a square. So this is also b square minus a square. And the numerator is also 0 because a is equal to b is there. So both these quantities cancel out. So it is actually a 0 by 0 indeterminate form is there. I should write which is of 0 by 0 indeterminate form. So that means I need to take the limit here. So let us take this b equal to lambda n is the zeros of, so let us take b equal to lambda n or zeros of jp of x and a be arbitrary. A you can take arbitrary such that a tends to b, because ultimately what I need is this a and b has to be safe. So I'm taking this b is this lambda n and a will be arbitrary which tending to b. Then this integration 0 to 1 x jp a lambda x jp b lambda x or ax bx dx will be limit a tends to b a into jp dash of a jp b of x b minus b into jp at a jp dash at b upon b square minus a square. So I'll have now, we can apply the L'Hospital rule here because it is an indeterminate form by 0 form. So by L'Hospital, we can say that this is equal to limit a tends to b. A, now we are applying this L'Hospital rule with respect to a. Okay, so a is the variable here because the limit is tending to a to b. So your variable is a. So a as it is, a derivative of this jp dash at a, that is jp double dash at a, jp at b as it is, plus the derivative of a will be jp dash at a, jp b. The same thing which we have here, that is the b is constant, jp dash at b is also constant, so only that this term will be there. So it is minus b jp dash at a, jp dash at b upon the b is constant, so it is 0 minus 2a. Now we'll just apply this limit a to b. Now this will not be a 0, so I'm just applying this a to b. So this quantity, that means this integration from 0 to 1 x jp ax jp dx dx will be, when you apply this limit to a, sorry b here, so that we got 0 to 1 x jp ax jp dx dx is equal to b into jp double dash at b, jp at b minus, sorry, plus jp dash at b, jp at b minus b, jp dash at b, jp dash at b upon minus 2b. Now what is jp at b and jp at b? It is a zeros that we have taken, that jp b is the zeros of jp of x. So that means this value will tends to 0 and this value will tends to 0. So only left is this one. So that means we can say that this is equal to 0 plus 0 minus b jp dash at b square upon minus 2b is there. So that's why this is b will be get cancelled out. You will have 1 by 2 and minus minus also get cancelled. Jp dash at b square. Now what is b? We have taken is a lambda n. So that is 1 by 2 jp dash lambda n whole square. So by recurrence relation now, which we have derived in the previous lecture, that is by recurrence relation, jp dash at x minus p by x, jpx is equal to minus of jp plus 1 at x. Now if you apply this jp dash, that is lambda n here, so this is jp dash lambda n minus p by lambda n, jp lambda n equal to minus jp plus 1 lambda n. But this lambda n, as per our assumption, that is we have taken this b is the zeros of jp of x, so that means that will gives you this jp lambda n is 0. So this is tend to 0. So what we have is the square of this quantity. So finally what we have, a square of this quantity, that is jp dash lambda n square will be jp plus 1 lambda n square. So hence this integration 0 to 1 x into jp lambda n x whole square dx is 1 by 2 jp plus 1 lambda n whole square, where lambda n is the 0 of jp of x. So which completes the proof of the orthogonal property of Bessel's function. If you have any question, you can ask.